I've got a replacement knob from Mauser. It's a replacement pot. It's significantly smaller than the other one, but I've managed to put in a spacer to get it in place, and it's the exact same size and has with regard to resistance value, it has the exact same sweep, so it appears to be good. So I'm going to solder everything in and get it back to how it was, except I'm going to replace this capacitor. Obviously there's no need to keep this one in place. I'm going to remove it soon anyway. The old pot used to have a standoff, which I've removed, and used the eyelet of that standoff to merge the old connections that used to be a part of it. It's gone now, but now the standoff is there, provides some rigidity between these three connections here. One coming up off that pot, meaning those two resistors, and this black wire here. I've yet to connect this capacitor here, which I'll be removing. This will be the first of the non-electrolytic capacitors that'll be replaced. I know a lot of these new polypropylene capacitors aren't going to be long enough to replace the existing runs, so I've pre-staged them with new wire, added the wire, put on some heat shrink, made it nice. Always paying attention to the markings that I'd made in a previous video of the outer foil. So the outer foil will be pointing to the lower impedance side of the circuit and will be able to fit back in the circuit. In this case, we can see here that this won't be sitting in like this, replacing that old capacitor. I'm going to be doing two of these capacitors right now immediately. One is obviously to satisfy this requirement, and the other one is for a resistor that I tacked into place on the bottom but did not perfectly seat in because it was put in so that it wouldn't have to be fully tacked in, so the capacitor could be removed later. So those two are going to be done right now. This one will be the first. Here we have a nice clean installation of the new capacitor. It's nice and taut. There's no slack on the line there. Got the old cap down here. Obviously we're going to be doing some comprehensive leak down testing. Not only am I going to be using the IT11, but I'm going to be putting an inline ammeter to see exactly how many microamps of current we're seeing at a given voltage. I've now replaced that second capacitor on the bottom of the unit and probably tacked in that resistor that I'd replaced in an earlier video. Now these two capacitors right here are replaced. I think I'm going to stop now, take a look at these capacitors, measure them. I believe their measurements with regard to capacitance appear to be okay. What I'd like to see is what the leak down voltage is. So I've got the modified test set set up. It's the IT11. I've got the magic eye on, but the camera's running right now, so you can't see it. But it's modified because I have the micro ammeter in line. It's going through the micro ammeter to the capacitor under test. Currently disconnected right now. This is set up for paper mica. Like I said, doesn't really matter because we're using the micro ammeter. Our test subject will be going up to 400 volts DC. First thing we're going to do is use this guy to measure the capacitance. I could use this. Reason I'm not going to do it is because I don't want to break down this whole entire test just to measure capacitance and reconnect it every time. So I'm going to test it with this, and then we'll go back to that. So let's do that first. 0.23 on the meter. That's pretty good. Like I said, I expected these in particular were not going to be too far off. To further complicate matters, I've added a voltmeter in place. When current flows through here, the way this power supply is set up is the voltage drops somewhat significantly as current increases, right? So to actually see what the actual voltage is, I've added a voltmeter here. The voltage on this assumes that no current is flowing, right? This power supply is not designed to actually power stuff. It's designed only to check capacitors. So you need to keep that in mind. So on electrolytics that heal as current drops, voltage climbs on this. So just important to know. We're trying to get everything close together. So I'll call out the dial, and then we'll look at what the actual is on the right in terms of voltage, which may or may not be a good connection because I don't really have an optimal connection. I'll try and fix this before the video. Okay, everything's sufficiently warmed up. I've fixed that connection. I made it more rugged. Let's give it a go. We're at 3 volts. We're seeing 2.6. We see current flow instantaneously as the capacitor charges, which would also be displayed on the eye as the eye charges, or you know what I'm saying. But here we go again. We see it instantaneously, and 6 volts, we're seeing 5.4, and we're seeing no current flowing, right? This is what we expect. Let me bring this light away from here. We can at least see the eye too. So you can see the meter fluctuate between we're looking at 0.1 microamps. So we're looking at absolutely nothing is basically what we're seeing. So we're gonna proceed, right? Try and get it out the glare out of the way. Get the camera, we can see everything. And this is 10, reading 9.6. You know, pretty much on the money since there's no current. 15, and you'll always see that current for just a second. And I will proceed. That's 25. $50. .4. You see, we're starting to see some leakage here. 0.4, 0.3. See if it settles down. And you notice that the voltage is not aligning itself to the dial anymore. Looking at mini limit, we see 0.3. We'll keep going. 150. .5, 200. Oh, 1 second. Stand by. The meter shuts off after a time. I'm going to hit discharge for a second. Make sure everything's safe. This is so very annoying. Back to microamps. And I will hit leakage again, turn everything back on. Let everything settle down. So we're seeing 194. We're up at 342. And we max out here at 389. If I go over at this point, I'll exceed it. And at 389, we are seeing 2.5 microamps of leakage. Right? So this is what we're seeing from this capacitor right here. Rated for 400. I would not call that excessive for this capacitor, though we could put a polypropylene up on here and see what that looks like at its rated voltage. So shut the background light off of this. This is a polypropylene, and it's going to do exactly what you expect. There's going to be no leakage whatsoever, right? So I'm going to have it down to paper mica, the strictest setting, right? This is going to measure like 0.1, 0.2 microamps, right? I set to leakage. Try and get everything in here. Everything's in the picture now, right? And I'm not even going to call them off and just shut this off, turn it back on. You know, very annoying. It saves my battery, so I'm not going to complain. This thing is going to settle down. We don't really care, right? I'm just going to dial this up. And we're going to go all the way. We're just going to max it out. 600, right? And this thing didn't even know there was a capacitor connected, you know, other than the charging points right there. And it's showing 0.3, 0.2, you know, this meter will settle down, 0.1. You watch that happen. It's like there's nothing there, right? From the standpoint of this meter, right, not having the ammeter in play, I would call that capacitor absolutely perfect. Now, if I remove this meter from the equation and I put this one in, I would also look at it in the same fashion and say this capacitor is perfect, right? Using my strict measurements that I've set up paper mica for in this. So let's do that again and run through this quickly and see what happens. So you can see that the test is off. It's on 0.2, 0.3, just sitting there, settled down. And the only difference I'm going to do on this test is I'm going to limit it to 400, obviously. It's not rated to 630, right? So I'm going to set it to leakage right there, and it charges up. And then we're just going to dial it up, right? So we're going to... And aside from the fact that you could see a little bit of artifact, like there's just a hair of leakage there on the paper mica setting, I would never even look at that. I would say this capacitor is just fine and move on, because this setting is so specific. You just start to see an artifact at 3 microamps, and then you get full closure. I think I have this calibrated at like 10 microamps. It'll be at full closure. So you can see at 2, it's almost completely faded now at this point on the scale. See if I could zoom in on that. I don't always get a good shot of the magic eye, but I should tell you right now, that's at 2. So 2 is like the cutoff point. There it is, right there. So right at 2, it hit 2.0 and it shut off. So, I mean, I would look at a capacitor like that. And everybody who knows my videos knows that I look at stuff, and if it's 1% out of spec, I immediately throw it out. And I would look at something like that and say I keep it in, So I'm gonna test the other one right quick using the same method. I'll also point out that the only variation in this test is this capacitor is only rated to 200 volts DC, so we'll only be ramping this up to 200 volts. So I'll try and get the glare away, and we will just literally just ramp this all the way up. This is sitting, the meter settled down to 0.1, and we'll go all the way to 200 right now. Oh, would you look at that? Yeah, that's a problem. That's 15 microamps. Yeah, that's not good at all. Oh, look, we found one. How do you like that? Okay, let's discharge and see our fail point. See, I'm not staging this stuff. I'm doing this the first time you guys are seeing this, the first time I'm seeing it. So let's bring it down to 3 volts and see if this is a total catastrophic failure. It's not. So leakage is fine. 10, 15. Yeah, so this is not. Yeah, this is 100 and dead. Well, I'll be. We do have bad caps in this unit. And that means for all the good ones we got, I could have one pulling. And it's not the 2.3 you're looking at that's bothering me. That's bothering me, right? So 15 is fully closed. Let's go to mica-lytic, right? Even mica-lytic or mini-lytic, sorry. 15 sits there. Electrolytic, you could have like a short circuit and still pass mini-lytic. It's terrible. It's like 2 milliamps or something. But right there, sitting at the 15, it's sitting there awfully close. But yeah, that's no good. Yeah, that's no good at all. Yeah, that's bad cap. Outstanding. Wow. Cool beans. I guess we are going through. I guess we are going through indeed and looking at these caps, because I got a bit uppity when I started seeing this, and then I saw that and I said, yeah. I know some people will say, well, 15 microamps. Well, yeah, 15 microamps already. Now we got something to talk about, because if I were putting it on my test set, like I mentioned, obviously it's good. You can see it discharge backwards there, but if it's half the rated voltage already, I'm going to see problems, and then yeah, we got an issue. How do you like that? Incidentally, it's worth mentioning that this 0.1 microfarad capacitor did measure correctly with regard to capacitance. The measurement was good. It was the leakage that was bad. All 4 of the 0.1 microfarad capacitors have been replaced from the rear board. They will now be tested for leak down and capacitance values. They've been replaced with these polypropylene capacitors. checking to see that the outer foil is in the correct position on the board. We're going to zip through the testing procedure on these 4 capacitors that I've removed. They are measured to 200 volts DC. This one is good. This one is also good. The third one. The third one is this test set does close at 3 microamps, fully closed 3 microamps. So you're seeing it's just starting to open up at 2.9. So this is at 150. So this is what I would call unacceptable with regard to leakage for this capacitor. So this capacitor would be considered a failure. But just to show you how well calibrated this test set is, right? I'm going to turn this light out of here. It's showing 2.9, 3.0, right? And you can see the eye, see if I can zoom in, is just fluttering between open and closed at 2.9 and 3.0. See if I can move this. See that? So this third one is a failure. So this capacitor would be considered no good. I'll move to the fourth one. Continue on with the fourth one as with the others. Starting it up. $200. There's no leakage. This capacitor is good. So 3 out of 4 of them were good. That gives us on the backboard a 25% failure rate, which is good enough for me for replacing all of them. So yeah. 3 more capacitors were replaced. This 600 volt 0.1 at the vertical input here has been replaced, and there are 2 over here. This one, this is a 0.25, and there is another one which I cannot see. I think it's on the other side. It's also a 0.25. But now we're gonna switch gears again and test these out and see what they're doing. In terms of their capacitance value, all 3 of them have passed the test. They are well within specification for capacitance reading. Now we'll do the leak down testing. Again, I'll quickly go through these like last time. The first 2 are rated at 400. I'll set it for leak down, and we will just ramp it right up to 400. Good at 150, 300, 350, 400. We're showing 3.8. 3.1 microamps. I'm going to call that one, that is good. That capacitor would be considered good by my testing. So next one. Next one is the same exact value as the last. We'll start our testing. We'll ramp up the voltage. 250, 350, 400 volts. We're showing about 3.8 again. This one by my tester would show this to be good. Minimal amount of leak down voltage, 3.2 microamps. The last one is different in that it will be measured all the way to 600 volts. So we will do the same test, but all the way to 600. So we'll start it up. Just slowing down to make sure that we're not going to have any shorts. 450, 5, 600 showing 8. It's going to drop a little. I've seen a lot, even on these dry capacitors. What happens is as current flows, it heats up a little internally, and any internal path for current to flow as it heats up. If it's caused by moisture, it'll sit here for a couple of minutes. You'll actually see a couple of microamps go down. Unfortunately, the way they are, though, as they soak up moisture again, it returns. So, you know, basically what you see is what you get. But if I would have let this sit here for about 5 minutes, I'm sure that this would continue to drop in current, you know. So this is what we got. But that being said, 6 microamps, still, as far as the test set goes, this is passing. Not as good as the polypropylene, but still 6 microamps is not really gonna do a whole lot to this circuit. These are the last 5 capacitors that have been removed from the unit. All of them are rated to 200, except for this one, which is 400. The capacitance of these have all been checked, and it is well within tolerance. So now we're going to check the leak down. This is the 400 rated one. Oh, yep, that's no good. We can already see that's a problem. I'm going to back it off and discharge that. It opens up at 100, 150, 200. You can see it's slow. Yeah, 250 it already closes. So 300 is 4.7 microamps. 350 is 6.3, and 400 is already 8.2. Yeah, that's no good. So this 0.01 is no good. This one will be measured to 200, and this one is good. Yeah, it took a bit, but yep, this one's good too. This one's good too. And finally, this one is good too. So only 1 out of 5 are bad, but that's 20%. So that concludes all the capacitor testing. We've completed the portion in this project of replacing all the non-electrolytic capacitors. Out of the 14 that have been removed, 3 of them have had leakage that was non-acceptable based on the testing that was conducted with the IT11. That being said, 3 was more than enough. It could be argued, however, that the capacitors were not running at their maximum rating, and if they were running at the voltage that was actually going through them, they probably would have been within acceptable parameters. That being said, we don't test components at the parameters that we think that the voltage will be flowing at a given time, but we measure them based on the values that are written on the outside. So fine, good enough for me. In the next video, I'm going to be shoring up the last of these things, the you know, the couple of resistors that needed replacing, the 100 that I'm going to throw in sort of loosely, enough to take some measurements and see if this is good for this circuit. If not, it'll be re-removed. Doesn't have to be permanent. Take some AC measurements here, see what they look like before we add in the rectifiers. I believe this is the rectifier for the CRT. There's no flyback transformer in this unit, but it does have this this high voltage rectifier, and then this is the rectifier that's used for the plate voltages and what have you. You can see down here they make their way down and around. That's for the next video, but we're going to call the capacitor portion of this finished. So that portion of the project is done.